So yeah, so let's move on now to the digital frontier, and kind of as returning to what we just discussed, in this kind of analog approach, I mentioned that we are encoding qubits in the superposition of ground and Rydberg states, but it's clear also, I think, sort of as was clear during the discussion, is not really the optimal basis for encoding. And the reason is because this Rydberg lifetimes is limited, and moreover, these Rydberg atoms in general will not be trapped, so also if you use blockade, then we cannot actually utilize fully the entire Hilbert space. So, and it was clear from kind of early days in this field that the right approach is to use these spin states, for example, hyperfine states of atoms for encoding, and then just, to store the atoms in the states, and then we use Rydberg states to excite the atoms only for a brief amount of time. But actually, for many years, people thought that while this is an interesting idea, actually in practice, it does not work very well. And the reason is that the fidelity of this kind of interactions in these configurations was actually experimental fidelity was relatively low. So, and actually it started to change about 5 years ago. And this was with an advent of something which is now called Levin-Pichler gate. And so what is it? So basically, suppose we just have a pair of atoms and we would like to make a 2-qubit logic gate. And so basically, the simplest way to do it is to imprint conditional phase on the state where, for example, both of the atoms start in state 1. And, for example, like if we imprint the phase pi, then it will be, control Z operation. So it seems kind of very simple. The ideas how to implement it go back to these original papers, 20 years ago, almost 25 years ago. But what really changed the kind of, I would say, the rate of the progress in this field was this idea of Harry and us. And the idea was to basically come up with the gate, which is very fast, but it also does not require individual addressing of the atoms. And I should say, and it's kind of relevant to the school, I mean, it was clear to us working, and I was still ITAMP postdoc, I spent, a couple of weeks trying to come up with the pulse sequence, which implements this. And there were some other, very smart people involved, and we all collectively failed. And it really took a new generation of the young scientists to really, solve this problem. And I think that means that there are a lot of opportunities, in this field. So, but kind of, okay, but another thing is that kind of I used to always, start my lectures with the kind of pronouncement of 5 things that you must know to very well in order to do research in this field at a high level. So, and it's 5 things you must know in quantum optics. So I did not do it because now I think, you can probably read on the internet, so what they are, but actually number 1 in this list is it's a 5 concepts, very fundamental concept. The first concept in this list is block sphere, you see, and so understanding this block sphere, and if you're interested, I can tell you about the other 4, but the block sphere is very fundamental. And actually, Hannes and Harry, really had deep understanding of this block sphere, and that's how they came up with this pulse sequence. So it turns out that actually, and that's the oversight which we made. So when I was kind of looking, and we were looking 20 years ago for this pulse sequence, we wanted to find one pulse, laser pulse, which would do this job, which we can plan imply conditional phase. So Hannes and Harry realized that actually it's easy to do if you have two pulses. And then you can use computer, and you can use optimal control to find one pulse sequence, it turns out. But so these two pulses are essentially kind of, the idea is the following. So in this kind of situation, you have basically four manifolds, or actually three manifolds de facto. One is the one where both atoms are in zero state. If you excite atoms out of one state, they will not be touched, right? There will be no dynamics here. So if you have one atom in one of the state or the other, then effectively you have a two-level system where just, you have one atom undergoing the dynamics. And you have a Bloch sphere associated with this two-level system. And actually, if you have both atoms in one state, so in principle, you can have two excitations, but due to the blockade, you can only excite at most one Rydberg atom. So you have also two-level system, you have another Bloch sphere, but in this Bloch sphere, because you start with state 1,1, actually the Rabi frequency is different. It's changed by square root of 2, right? Because basically, if you have two atoms, the probability to excite one atom or another, it's like twice one atom probability. So in the Rabi frequency, it scales like square root of 2. And so basically now what the task is, you want to essentially devise a pulse sequence where, you're starting from the 0, 1 or 1, 1, you go into the excited state and come back, with unit probability. But in these two cases, you want the relative phase between these two cases to be exactly pi, or whatever value you want. And it turns out that there is this sequence of two pulses which exactly achieves that. And kind of the idea is that you basically, excite the atom with some detuning, and basically, when you do it, and then kind of, change, flip the phase of this kind of Rabi frequency, then what happens is that, you basically come back on this kind of other, trajectory on the Bloch sphere, and you can, because there's now these two Rabi frequencies are different, you can basically, find the detuning, kind of a magic value of detuning such that the exact phase rotation is exactly pi. And so that was the Levin, Pichler insight. And actually what happened is that once they had this idea, literally that same day, Harry went to the lab and implemented it, and it actually resulted in a fidelity, which error, or effectively an error rate, which was like factor of 5 lower than anyone has ever achieved, So, okay, so that's sort of, what started, if you want, the kind of recent, renaissance in this quantum computing using Rydberg atoms, this very simple idea. Okay, that's one thing. And actually, there is another thing which I also want to, which is also similarly important. And this is the idea of reconfigurable architecture. So, as I already mentioned, if you store atoms in a hyperfine state, and in particular for rubidium-87, as correctly pointed out, this hyperfine splitting is exactly 6.8 gigahertz. So the T1 time here is basically limited by vacuum, T2 time is typically a few seconds, and it's basically limited by how hard you try to sort of dynamically decouple this state. But you can store this atom in tweezer for, as long as your vacuum allows you to do. But actually, what is remarkable is you can also take this atom in this tweezer and move it around while preserving coherence. And this gives rise to, and kind of that's the illustration here. So suppose you, for example, start with this kind of pairs of atoms, and you entangle them here, for example, through this Levin-Pichler gate. What you can do next is then you can just move these atoms, instead of measuring them here, what you can do, you can just move these atoms apart and then check if you have entanglement or not. And actually, in this case, you see basically the entanglement is completely preserved. And so this gives rise to this idea, which we call reconfigurable architecture, where basically the connectivity of your system is kind of a dynamical, variable. So it's actually very special, because if you think about, for example, how your the processors, conventional processors are made in your cell phones and and in your tablets and your computers, what people do is they design, they lay out these transistors, what should be connected to what, and they send it to the fabrication. In fact, they use optical lithography, very similar techniques to make it. But the connectivity, the architecture of the chip is fixed at the design stage, So here, the connectivity and architecture can be a living organism. It can change during the computation, while the system preserves their coherence. And it's actually special for multiple reasons. So one of them allows for the so-called non-local connectivity. It allows one to connect one qubit to any other qubit, and in particular, it allows for like parallel, very efficient classical control. And as I already mentioned, control is a key challenge, and this really allows one to solve this problem. So, so with this kind of, so does it make sense? Okay, maybe let me just ask if there are any questions. Yeah.
The reason the atom keeps for coherence when moving the laser perhaps is because the moving is adiabatic.
Yeah, so I mean, the main reason is that basically this kind of electronic degree of freedom is completely decoupled from motional degree of freedom, right? So basically, even if atom starts to slosh, I mean, it does not slosh. It does not, the sloshing is completely independent to the very high degree from its spin state. So, of course, if you start moving, you would like atom not to kind of slosh too much. That's why you would like to keep it kind of reasonably adiabatic. Even if atom starts to move a little bit, it's not a problem, right? So that's yeah.
That improvement was given due to the blockade. To make 120 micrometers, that's very large blockade radius. So how are they studied now?
No. So okay. So here, so yeah. So what is happening here? You entangle atoms when they're close, right? And what you do, what these two curves correspond is one, you entangle atoms when they're close and you just measure directly. Or you entangle atoms and move them far away and then measure. Yeah. So and that's the point. So basically, here or there within blockade radius, here they don't interact. And so you can now utilize this digital character of, so this is that's what that's what goes into it. So, okay. And so this kind of approach allows a lot of kind of cool possibilities, which many of them we kind of explored. So one is you could, for example, combine analog and digital evolution. You can use, analog evolution to entangle particles, but then store the information in these hyperfine states and do things, for example, swap test, which I think, Christian probably talked about, so we can measure entanglement entropy. You can also, kind of use these techniques to really have new tools for many body physics, but maybe kind of more kind of forward-looking. It really allows one to think about new models for quantum simulations, and actually I might, if I have time, I will talk about some recent work. So actually you can think about some kind of implementing, for example, various topological matter and lattice gauge theories, and also you can also think about applying these ideas to simulating high energy models. So as I already mentioned, I will actually, if I have time, I will talk about like some of our very recent experiments involving the simulation of the topological systems of the Kitaev model at the end. So, but basically, you can also combine it, with various kind of tools. For example, you can combine it with Loki engineering. I don't know if someone talked about that in the school. That's my bonus kind of lecture if I have time. But at the end, in all of these approaches, the key challenge and the limiting factor will be errors. So if you do these gates, there's always a small error probability, and basically you need to control this and kind of mitigate these errors and eventually correct these errors. So this brings me to something which I think has been discussed already, and this is like the quantum error correction frontier. So this is one of the like challenges at forefront of this field, and I think Harry gave, I hope, reasonable introduction to that. So basically, current errors in these devices was like 10 to the minus 3. So it actually allows us to do like 10, also to do like 1,000 of gate operations, 1,000 interactions. But I mean, eventually, many applications will need like 10 to the minus 10 or even lower error rates. And whereas initially, some people would have thought that quantum error correction is fundamentally impossible because in quantum mechanics, you cannot copy the state. You cannot duplicate quantum information. Moreover, if you use redundancy, you have to measure. Usually, if you measure, you destroy the state. But actually, nevertheless, it turns out that quantum error correction is possible. And already theoretically, this was kind of a remarkable development, and you basically, what you do, you use entanglement to store information locally, and then you use something which is called stabilizer measurements, which I think Harry has described to detect local errors. But of course, by delocalizing quantum information, you also, make it, you make it, more robust against accidental, manipulation, but it also makes it hard to manipulate it deterministically. And so basically one example of that is the example of toric or surface code invented by Alexei Kitaev in 1990s. So this toric or surface code is basically a product of two classical repetition codes. So did Harry talk about this a little bit or not? I see. Okay, good. Okay. And so basically what you do here, you kind of encode information on a grid of the lattice with the length d, where d is the so-called code distance. It determines the degree of protection, and basically to check if you have an error or not, you measure this kind of local, so-called stabilizers, products of four operators. And what happens is that if, for example, physical, qubit flips, in this case, for example, undergoes a flip, bit flip, so you'll have two stabilizers, two Z checks, which will actually light up, will turn from +1, how they should be in the ground state, to the -1, and in such a case, you can just detect this error. And the idea is that if you now start making the lattice bigger, you have more checks, larger code distance, but also more opportunity for errors. And that's where this notion of threshold comes in. So basically, it turns out that there is a phase transition. If your error is below a certain threshold, then the bigger is the system, the better it is, otherwise it's the opposite. And this threshold for this surface toric code is actually typically about 1%. So basically, if your errors is below 1%, you could have an opportunity to improve the situation. But while this was really this theoretical breakthrough, which really caused the field quantum computing to take off, and it's clear that eventually we'll need to utilize techniques like this, it's also clear that these things are very challenging. In fact, many people, really many like very smart people, who are actually sort of did really groundbreaking experiments on entanglement publicly doubted, when these ideas came that they will ever become practical. So this, like using this reconfigurable architecture, allows us to actually very effectively realize this kind of error correcting code. So this is an example already a couple of years ago where we realized this toric code actually on a torus. And you could say, wait a second, how can you do it? It's kind of seems hard because with the two-dimensional architecture, how do you realize something on a torus? The idea here is the following. So if you start with kind of lattice of atoms where you have data qubits which are stationary. So what you need to do, you need to basically make this kind of stabilizer checks, and this typically is done by these ancillars. And basically, if you now have these ancillars which can move, so what they can do local checks, but they can also go all the way across the system to somehow close the stores, right? And that's the idea. That's a movie which actually corresponds to implementing this story called on the Taurus. And the details here are not important, so I will talk a little bit more about other examples. But the key thing is that this entire circuit is programmed by specifying an SLM profile and this AOD waveforms. There are basically two control voltages, and one control voltage moves these AODs in up and down, and another one is left and right. And so, with these two control voltages, you basically implement, in this case, two logical qubits. One of them going, around one way, and another one is going another way, right? So basically, for each of the logical qubit, you have just one control parameter. And this kind of control, efficiency is actually super central to implementing, quantum error correction. And I would say prior to this work that I'm going to tell you about, it was really overlooked, So, okay, so with this kind, okay, so to kind of, I will tell you a little bit about some error correction experiments at Harvard, which we have done last year. I think Harry talked a little bit about work at Quera. I mean, both of them utilize similar systems. This is a system which we first realized at Harvard, and then it was eventually implemented at Quera. So, as I already mentioned, the key here is a special light modulator which creates the traps and these acoustic deflectors which move the qubits, rows and columns. So this was a third generation of our system at Harvard, which had, larger systems, high fidelities, and actually kind of more advanced control. So the key upgrades which resulted in this new generation are first high fidelity gates, which are now have error rates more than 0.5%. So basically below, for example, a surface code threshold. And this was realized by basically improving, some technical things, for example, increasing laser power to make these gates faster. So you want to go in and out of Rydberg state as fast as possible. But there was also kind of a new advances in the gate protocol. So, for example, using optimal control techniques, one can actually convert this Levin-Pichler scheme into one pulse, where you basically chirp, you change the retuning of the laser pulse as you excite. And that actually, resulted in substantial boost of the fidelity. So one also in our system now, one can also do arbitrary single qubit operations. And the way how we do it, we have another set of these acousto-optic deflectors which can illuminate different patterns of atoms and actually do Raman, transitions basically of individual atoms. And one other important thing is this realization of mid-circuit readout. And actually, the way how it's done is we use this kind of atom motion. So we basically can just take atoms from the zone where we store them and move it to a separate zone and just image them there. And so these three ingredients, really enable this kind of recent generation of experiments. So, so in particular, this work that we've done about a year ago, so utilizes this kind of zone architecture. So where we have a place to store qubits, where we have an entangling zone, where we basically can, entangle atoms in parallel, and not just one pair at a time, but, hundreds of pairs at a time, which is a huge, advantage. And then we have this readout zone, and here the important thing is that basically we would like this, entanglement to have as few calibration parameters as possible. We want, and the fact that atoms are identical and this kind of Rydberg blockade is robust, kind of almost digital interaction is a key to that. So, okay, any questions about this kind of a little bit experimental side things? if Harry talk about this. Sorry.
Actually, you said the motional degrees of freedom proof doesn't matter when moving the atom, but it truly matters if you do this readable not blockade, but readable interaction.
Well, that's the point. That's where this blockade comes into play. So if the atoms move, right? So then the position between them fluctuates.
Yes.
Right? So if you would just kind of excite atoms in a Rydberg state and wait to accumulate this conditional phase shift, then this uncertainty in this motion would almost certainly result in decoherence. But if you use this blockade mechanism, right, if the atoms are close to each other, even if they move a little bit, so long as they are under blockade to the leading order, it does not contribute. It can contribute to some high order, but it's much less important. Yeah. So okay, so the key element for this kind of logical processor is the idea of kind of essentially departing from conventional sort of paradigm where you really want to control each physical qubit individually to actually controlling logical qubits. And I will illustrate it based on this example. And this is, and I'm sorry if Harry talked about it, but it's so central, which is, is very important on this kind of so-called transversal CNOT operation. So imagine you have two logical qubits, for example, encoded in this kind of surface codes. And in each of them, the quantum information is delocalized. So if you want to do a gate between them, somehow you want to every qubit on the right to feel or to know what every qubit on the left is doing, right? Because that's kind of the idea, right? You need to, information is delocalized, you need to make sure each qubit on one patch sort of knows about what the other is doing. And for that reason, doing the gates is actually challenging. So there are these techniques like lattice surgery that maybe Harry mentioned, or braiding, or you can just take qubits and try to braid them. But they are basically both, very complex and kind of also error prone. So instead, there is a technique known as transversal CNOT operations, and in this technique, you basically directly interact this delocalized degree of freedom. So the way how it's done, literally, you pick up these atoms, bring them on the top of the other, and basically, do CNOTs on all pairs of atoms at the same time. So that's kind of almost a definition of transversal CNOT. And it actually turns out that, just by exciting them in the Rydberg state, and then, if you bring them apart, this actually implements transversal logical operation between logical qubits. So this operation has a lot of features. So it's, for example, inherently fault tolerant. Errors cannot spread within a block. So it also can be long range. You can interact kind of any logical qubits, but more importantly, so you can see now that because all qubits in each block receive basically the same instruction, you can really literally treat each of these logical qubit as a kind of macro atom, as a macroscopic atom. And they all are moved in the same thing. And by using these optical multiplexing techniques, we can literally with one knob here do the logical, operations between these two different atoms. So, okay, so the example here is this kind of logical CNOT with a surface code. Okay, I don't know if Harry showed this. Maybe not, I don't know. Okay, so it's actually very simple. So you prepare one of these blocks in a plus state and another one is 0 state, and then just do CNOT, And the way how you do it, you kind of measure Z stabilizers in one of them, measure X stabilizers in the other, and then basically bring them on the top of each other, do CNOT, move them away from each other. And the key property that we want to study is that if we now increase the size of each of this logical block, the operation, the error should reduce. And this is actually extremely non-trivial because each of them are entangled states. So usually if you create a large entangled states, it becomes more fragile, but actually, if you do it correctly, and if you measure the syndromes, that's a key kind of property of error correction that it really should improve as you grow the scale. Okay, so first off, what we can do is in this distance 7, we can see that these two logical qubits are clearly entangled. So we measure both in X and Z basis, and we see that they're entangled. And moreover, if you look at the scaling, the error decreases as the code distance grows. And that's really the key feature of the error correction. So, okay, now there are some caveats here. So first off, in order to obtain these results, it turns out that we actually have to decode the information in a very special way. So we decoded this information not just by looking at individual qubits here, but at looking them jointly. And at the time, when we have done it, it was really done out of necessity, because if we did it in a conventional way, the error grows, right? So clearly this correlated decoding is very important. So second, and this is sort of like maybe another caveat here, we just did one operation and measured it right after. So of course, in practice, you need to do multiple operations and make multiple syndrome extraction. But I mean, this clearly shows that this approach works, that basically entanglement and quantum operations of logical qubits improve the code distance. And moreover, the fact that one has to do correlated decoding was a bit of an experimental discovery. And actually, we've since then learned that it's very, very important. And maybe Harry talked about this algorithmic fault tolerance and so on. But I would like to emphasize that this was really first done actually in the experiment out of the necessity. So you can do also a wide variety of other experiments. So for example, you can prepare some states fault tolerantly. And this is an example of the so-called steam error correction. So where you basically make two copies of state. In this case, it's a color code. It's the same color code which is shown here, which Harry probably talked about. So, but what we can do is if we make two copies of them, we could basically encode each of them non-fault tolerantly by using a circuit where you can make gate errors and so on. Then you can make one you can use one of these copies as a kind of a flag to check if the other one was prepared correctly. And the way how you do it, you do transversal Hadamard gate, and then you do transversal C0 or CZ gate, and then bring them apart. And what you do, you basically measure one of these qubits. And so if both of them were at 0, so this has to be 0, right? But if this one was at 1, then you would actually see that it was, it had an error. And so that way you can, for example, like prepare the state, better than you can prepare a physical state, right? So this is a so-called fault tolerant state preparation. And while things like this has been done previously, the advantage we have now, so this actually data for, done with 8 logical qubits, basically 4 logical pairs, and once you have 4 prepared qubits, you can then, basically start, doing operations between them. For example, you can entangle them and prepare, small cat states, And here again, you can prepare them non-fault tolerantly, and prepare them fault tolerantly, or you can also start doing various kind of tricks. For example, when you do these experiments, you have information about these kind of flags of this preparation stage, but also when you do decoding, you have access to the stabilizer measurements. You can use the stabilizer measurements able to do error correction, or you can also use it to error detection. So for example, you can, given you have certain stabilizer pattern, you can just decide to disregard this data. So in this case, it becomes an error detection. And actually that way you can boost fidelity to basically almost 1 by just rejecting small amount of the data. So, I mean, there is a kind of like entire story here about how you actually measure even GG state. So it actually turns out that you need to do tomography. You cannot do, for example, like Ramsey experiments with this. So it really shows that this kind of logical qubits are kind of different beasts, they're very different from the kind of physical qubits. And you can also do like, for example, things like involving teleportation of these logical qubits. For example, if you prepare a GG state, and measure one in the mid circuit in the middle, you can actually then, prepare and do some feed forward. You can prepare Bell state of this outer two qubits, and this is in this case it's done by, for example, moving qubits, one of the logical qubit to a readout zone and measuring it and applying feed forward operation. So basically, these are all examples, of what one can do with this type of system, and it really kind of sort of brings us to this point where we sort of entering this kind of era of what we call early fault tolerant quantum computation. So I mean, we can suppress errors, but we cannot yet suppress them to 10 to the minus 10. But in this kind of era, it's kind of super important to think about these problems from this point of view, which we sometimes call co-design. So basically, what it really means is that if you want to implement certain algorithm, so you have to really pick the right type of error correcting code to encode this algorithm. You also have to think about, how to compile them and how to decode information in the right way. And this all has to be sort of co-designed with these native hardware capabilities. So actually, I mean, it's very clear that in the next maybe 5 to 10 years, that's the only way how one can really make progress towards like, really useful application of systems of this type, So maybe, okay, so maybe just before I go on, are there any questions about this kind of simple few logical qubit experiments?
So a very broad question is,
Yes.
so we actually start the whole thing by actually having two qubit entanglement, so it's more like a Bell state-like entanglement, and then we actually build up logical qubits which can then have GLC entanglement, right? Or non-Gaussian like entanglement.
Okay, so you specifically referring to this, right? To this, for example,
Yes.
to this. So okay, so the way how, let me just, sorry. So the way how you do it here, you start with this kind of atoms in the surface code, so which initially are completely unentangled. So what you do to initialize them, you basically first measure some of the stabilizers. And for this specific experiment, you measure Z stabilizers for one qubit and you measure X stabilizers for another qubit. And they prepare you in these two different, into two different states, plus and zero. So at this point, they're independent. They are not between them. There is no correlations. And so then what you do this kind of transversal logic operation. And that's when you entangle them, right? So these are all, at this point, these are all so-called Clifford operations. So so this characterization, whether they are sort of Gaussian or not, I mean, it's not really, I mean, Gaussian states typically refer to as continuous variable states, but I mean, these are all Clifford operations in this case, yeah. So, and I mean, I will talk about non-Clifford operations in a second. So to have non-Clifford operations, yeah, okay, it's a separate story, but we'll talk about it in a second. Any other questions? So yeah, I mean, okay, so it's very nice kind of segue into the next part of my talk, which is precisely about this. So all of these things are, all of these experiments involve Clifford operations. With Clifford operations, you can actually prepare some very complex, entangled states. But it turns out that the output of the algorithms where you have only Clifford operations is something which you can predict very efficiently classically. And I don't know if Harry talked about this a little bit. Christian. Okay, good. Okay, so basically, and the reason is fundamentally you can just propagate. And if you look at operators, you can just propagate them, and it's and you can track the operator propagation. So, okay, the question which I would like to now ask. So it's kind of going back and forth here is not reciprocal, not unitary. So, okay, so I would like to specifically ask about this implementing non-Clifford operations. And so far I've talked about these 2D codes with Clifford, which is X, Z, Hadamard, C0 is a Clifford group, which can be simulated classically. And this really, what gives quantum computers the power is this non-Clifford operations. But actually, it's known that in general, generating this magic or this non-Cliffordness is challenging. So, for example, there is something which is called Estin-Mill theorem, which basically, you can prove that you cannot have a universal set of gates which are transversal. So there are several approaches to deal with that. So one of them is this kind of magic state distillation, which Harry has talked about. But actually, it turns out that there is another approach, and this is going beyond 2D. So, and in particular, if you sort of, don't want to have completely general evolution, the question is, can we generate efficiently states with a large amount of quantum magic? The answer, it turns out to be yes. And the smallest kind of possible instance of that is a three-dimensional code, which is the so-called 832 code. It's actually a color code, but in 3 dimension. And it involves 8 qubits, which are sitting at this kind of nodes of this cube, which can encode 3 logical qubits. And the code distance is 2 here, so that means it's actually it's error detecting code. So it's actually error correcting code for one type of error and error detecting code for another type of error. And so basically on this kind of cube, you can determine, so the kind of the stabilizers are, different kind of products of this, of this, of the sides and kind of, and some of these kind of edges, local operations. So they just groups, they're just product of operators similar, to what we have for 2D codes. But there is one kind of important difference is that it turns out that because it's a 3-dimensional code, you can implement non-Clifford gate, CCZ gate, between these 3 qubits, which are stored within these codes, literally by just performing single qubit rotations, by basically just applying T gates on some of these, qubits within this cube. And so that actually CCZ gate is non-Clifford operation, so it allows us to sort of inject some magic. And then what you can do, you can also do CZ operation within the cube, and you can do C0 operations between transversally, between these cubes, so, and that allows one using this kind of approach, albeit with error detection, not with full-blown error correction, but with error detection, to really, implement quite complex circuits. So the specific circuit, which I will now show here, involves encoding first the qubits in a logical state plus, and then doing basically parallel operations within each block, which will be CCZ and CZ gate, with essentially just rotating individual qubits within this cube block, and then do parallel interblock nodes with motion, and then repeating this, multiple times to actually generate a lot of magic and generate a lot of entanglement. So and eventually measure this in the X spaces. So actually this implements the so-called scrambling circuit, a circuit which generates a lot of entanglement, which is somewhat similar to this quantum supremacy work that Google has done, but there was a random circuit. This is not a completely random circuit. In fact, what we kind of like to do, we like actually making cubes out of cubes and making cubes out of these cubes. So it's actually the kind of this logical connectivity will be this hypercube. So this physical connectivity will actually be quite complex, but essentially this is the kind of things which we want to implement. And so it turns out that this algorithm implements a class of circuits called instantaneous quantum polynomial circuit, which actually is a scrambling circuit, which is, for large number of qubits is classically hard to sample from. This is one of these quantum supremacy circuits. So and so what we'll do sampling from the circuit. So and actually it will be essentially looking at probabilities of each logical strings, and this should look like a speckle pattern. So in fact, what's shown here is an example of a circuit for 12 logical qubits, a small number, so you can still show each of the string probability here. So theoretically, this specific circuit should implement something which is shown here in this shadow with these different kind of probabilities. So now if you don't do any of this kind of error correction or error detection, this is a raw data shown here in blue. What you see is, well, maybe this biggest string has some resemblance, but I mean, it's really hard to see if this is really, if this raw data represents anything closely resembling what theory predicts. But actually, if you now start, doing this error detection, and in this case, literally it means just, selecting some data where, more and more stabilizers are in a correct value, what you see is basically a shadow of this circuit emerges, which really in this case, for high degree of error detection, really resembles very closely this kind of ideal result. And you can quantify it in different ways. For example, you can use this do this logical XCB. It's this kind of metric which Google also uses. It kind of is connected to fidelity, basically, of the circuit. It's not quite fidelity, but you see, basically, if you do a lot of error detection, basically approaches 1, And so the result with error detection, we are close to this to the ideal state. But of course, we don't need to stop at this 12 logical qubits. So in fact, we went all the way to 48 logical qubits. And this is actually a logical qubit circuit, which is, which we use. So this is a connectivity, which is extremely complex. And so what you see, even for this logical qubit circuit, basically this error detection still works quite well. So the fidelity of logical XCB here is not 1, it's kind of 10%, but it's actually a large number for the complexity, for the circuit of this complexity. And so that really indicates that these methods, this error correction works here for this kind of complex algorithms. And this is actually a movie which shows how we generate this kind of circuit. It's still probably by many measures the most complex quantum circuit implemented to date on any quantum computer. So what you see here, we start kind of entangling things locally, and then we sort of do it more and more globally. Then eventually we'll run out of space in the entangling zone. So then we bring another pair, entangle it more globally and kind of more globally. And then eventually what we'll do, we'll bring these qubits from storage zone and entangle them all together, right? So that's a kind of a bit of a hierarchical approach. And one can also ask, okay, so what can one do with this type of, it's a kind of it's a random circuit which generates entanglement, but what can one study? It actually turns out that this circuit has special property. It's what's called fast scrambler. So it actually scrambles quantum information, generate entanglement at a maximum rate. And you can actually study that by measuring entanglement entropy by using 2 copies of the states. So basically, if you have 2 copies of the same state, you can really compare them by making, for example, Bell measurements, which is in between each corresponding qubit, and you can use this to, for example, measure things like entanglement entropy. And so this is a kind of the result, so there are 2 copies of 12 logical qubits. And so what you see is that if you don't use any error correction, or detection in this case, if you kind of increase the subsystem size, this entanglement entropy keeps growing. And indeed, the larger system you have, the more entanglement entropy, it contains, because it's entangled with qubits inside the chain, also entangled with environment. But actually, if we start now using this error detection, the remarkable thing which happens is that once you reach half of the system size, all of the sudden system realizes that its global state is largely pure. And so basically it turns around and just has this kind of page curve, shape associated with that. So this actually really shows that, these logical qubits are kind of already useful for probing physics of this entangling complex system. And I think there are really exciting opportunities here for using this kind of fault tolerant processors. So, okay, so this is actually was work actually at the end of 2023. So it really, like last year, was very exciting because there was this quantum error correction was pushed along different directions. So as I said, we've done some complex circuits with logical qubits. There was some nice work also with ion traps, but actually also in these Google experiments, they just used 1 logical qubits, but what they did many rounds of error correction. So it sort of pushed this work in a complementary direction. And I think it inspired new theory concepts like this algorithmic fault tolerance. So for example, the use of correlated decoding, it turns out allows one to essentially outsource a large part of error correction from the quantum computer to a classical coprocessor. And I think Harry must have talked about this, right? Did he talk about this algorithmic fault tolerance or not? I see, okay. But okay, so it also, but he almost certainly talked about this magic state distillation. Yeah. All right, so maybe I just kind of this algorithmic fault tolerance, like I will just review it briefly and maybe we should make another break, So I mean, the idea here is the key idea of this algorithmic fault tolerance is very simple. So if you do these transversal gates, then this error propagation, the thing which really kills error correction is error spreading. So if you had some errors in your initial block, which, you sort of did not detect, initially, if you do some logic and if this error spread, then you are sort of done. You cannot do anything. So for this reason, in the typical approaches, what you need to do, you need to make multiple rounds of syndrome measurements to really make sure that you don't have any errors. But in this kind of transversal gate architecture, if you have errors, they will propagate, almost deterministically. If you had an error in one block, it will actually propagate to exact known location in another block. And the same with the errors. And so basically, if you now start decoding this kind of circuit by keeping track of these so-called hyper edges, so it immediately allows you to actually track these errors in a much more efficient way. And this is, for example, like we already also saw it in this kind of GAG circuits. So basically, you can basically undo the propagation of these errors by tracking them. And of course, if you do multiple rounds and a lot of gates, this entropy will be build up. So you need still to do this periodic checks But it turns out you need to do much less often than in a kind of conventional architecture. And we now looked at kind of couple of examples. One of them was looking at a kind of Clifford circuits. Clifford circuit is actually very clear that you need a you only need to check these errors kind of infrequently. In fact, in this case, you only need to check it after only a few rounds of gates. Conventionally, you need to check it, d times after each round of gates, where d is a call distance. But actually, what the work of Harry and others, what was remarkable is that it turns out it can be generalized to these non-Clifford circuits. And this actually is quite non-trivial development. And basically, this is kind of it has significant implications for example, the resource estimates of the logical algorithm. So basically, doing these experiments, is useful because we learn, about these errors and so on. So, I don't know if Harry also talked about LDPC codes. So maybe this is, so basically the outlook is we would like to actually now start looking for new codes other than the surface code. And particularly the problem with the surface code is very low density of encoding. So you just have 1 qubit, but it actually turns out if you have this non-local connectivity, you can actually do a lot more. You can actually use this variant, so LDPC codes are the type of codes which are used now for cell phone. It's actually used in 5G classically, So it turns out you can generalize them to quantum domain. And this actually is a kind of very exciting, also frontier where, one could really, have significant saving in sort of, in terms of kind of overhead and so on. But okay, so this is something, maybe it's a good topic for discussion. So maybe this is here a good time to stop here, maybe make another break, but I'm happy to answer any questions you guys have. Yeah.
Have you been looking at like a quantum Tanner code for the LDC or LDPC air connection codes?
Sorry, what's the name?
Quantum Tanner codes that was recently. It's like a quantum version of the classical version.
I see. Okay, I mean, I don't know very much about that, but so there are a few types of efforts. So there was this work by IBM where it's they use the so-called bicycle codes, which showed kind of sort of favorable thresholds. But for example, like, in terms of like when you start, I mean, the real challenge with this QLDPC, so we use hypergraph product codes here. So the real challenge is that, with these QLDPC codes is that you basically encode information non-locally, and you basically encode a lot of qubits in the same block. So to do quantum operations between these codes is actually quite non-trivial. In fact, has been considered to be like a big challenge, and so some of these different codes. So basically, in order to evaluate which products are good, and not or not, so you have to of course, make sure that they have thresholds which are reasonable and not too low, but B, that the gates that you can do within these codes should be relatively easy and don't have too much overhead. So these are the two sort of important considerations, but it's a real frontier, yeah. Yeah.
In simulations of I guess these kind of structures that are seen, cross entropy becomes almost unfeasible to calculate past 48 logical qubits.
Yeah.
Do you know the I guess a measure that can extend past that kind of simulatory threshold for larger numbers of logical qubits?
Yeah, so it's a very good question. It's kind of maybe it's a part of the broader question of how do you benchmark these logical qubits experiments. So first off, you know, and there are different kind of directions here. So one of them, benchmarking kind of any kind of circuits, sort of which involve like, you know, let's say something which is on order of 100 qubits, physical or logical, is hard, and this is fundamental, right? Because basically tomography, quantum state tomography is exponentially expensive. So kind of along that direction, there are these efforts to develop this kind of, you know, algorithms for verifiable kind of quantum supremacy or quantum advantage. And you know, one example of that is Shor's algorithm, right? You know, if you do Shor's, if you can factor, it's easy to check, you know. And so there is some effort now to try to actually come up with other examples, which would be sort of, you know, algorithms which are hard to kind of go one way, but easy to verify. So that's one direction which is going on. But specifically for logical qubits, you know, even for simple cases involving just a few kind of gate operations, benchmarking these logical qubits is actually, turns out by itself, is really an open problem. And the reason for that is that these logical qubits are not just two-level systems, right? They're sort of, and in fact, they only exist on paper as logical qubits, right? So, and you need to really think. And so, for example, like, you know, if you do physical qubit benchmarking, you could say, oh, you some kind of randomized benchmarking, and you have gate, you have spam and gate, you know, gate fidelity, you know, and you just can decompose them. It's not possible to do it for logical qubits. So this actually is a real frontier, and I think people kind of underappreciated the challenge, you know, in particular to come up with the benchmark which will make sense in the limit of large circuit is actually quite non-trivial. And, you know, one potential measure of that is how much entropy you actually can extract. So which, I mean, this, like, so the fundamentally what quantum error correction is doing is extracting entropy. You know, it's like a refrigerator, right? So, and, you know, if you can quantify that, it might be the best way to do it, but it's completely open frontier. And yeah. Okay, should we make, maybe why don't we make 5-minute break? No, we cannot make it too long because otherwise I will.
That's,
Yeah.
That's third action. Thank you.